For this video, I'm going to introduce you to logic and sets. So first what I'd like you to do is look at this diagram, which is a Venn diagram that you may have seen in some previous math course. Now I want you to think about all the things you know about Dr. Noah, who is this kind of point sitting right outside of those circles. So think about some things that you know since he does not belong into any of those circles. Jot down some of those things and push pause, and then check back into what some classmates have said. So some classmates have said that he is not a woman, so then they might say that he's a man. He is not under 6 feet tall, so that would mean that he is tall, more than 6 feet. Because if he was under 6 feet, then he would live inside this circle. Now, it shows that he does not live inside this circle, which says older than 30. So that means that he must be under 30. And what else might we know? He's a doctor. And so this picture actually tells you a lot of information about Dr. Noah. And what we've been using is some Venn diagrams to kind of understand some logic about where he would or wouldn't fit in. So we're going to explore this a little bit more. And first we have to understand some different terms that you're going to see within logic. So the first word that we have is statement. And a statement is a sentence that is either true or false, but not both. So a statement could be Dr. Noah is tall. That is a statement that could be either true or false. In this case, if we're following the Noah in the diagram, he's over 6 feet tall, so we'd say he's tall. So actually this seems like it would have a truth value. We could say 2 plus 3 equals 4. That's a sentence. It can be either true or false. In fact, this is actually a false statement. Now, something that's not a statement would be saying something like, oops, I can't spell. He is tall, because we don't know if that's true or false. It depends really on the he is, so it's not descriptive enough there to be able to tell if it's true or false. Or maybe something like x plus 2 equals 4. Again, we don't know if that's actually true or not because we don't know the value of x. So it's kind of like there's missing information, so we can't determine if it's true or false. The next one we're looking at is negation. The negation of a statement is really saying that we have the opposite truth value. So a lot of times what you're going to see is using the letters P and Q for statements. So look what it says. The negation of a true statement is always got to be a false statement. So if P is true, then we're going to use this notation. It's like a little squiggle. Sometimes you'll see that. Sometimes you might even see something like that. But those basically mean not P. So like the opposite of P. So if we say it is hot, the negation would be, well, it's not hot. So a statement and its negation have to have opposite truth values in all cases. So if we say that statement P is true, then not P must be false. If we said the statement P was false, then not P would have to be the opposite, which would be true. So we've just completed a table on negation. And so really what happens is the not makes us have the opposite truth value. A few other terms that you're going to see are quantifiers, which we use these a lot of times. They come in the form of these words: all, some, every, there exists, or no or none. There's universal qualifiers, and then there's the existential qualifiers. So the universal qualifiers are really looking at the first couple here. We have the all and every, so they're like universal, saying everybody, everyone. Existential is really saying like there exists, there is one, at least one. So we're going to look at the negation of some very common statements, and really they kind of go back and forth between a universal quantifier and existential. So if we say that some A's are B's, the negation of that would be to say no, like that's a universal thing. No A is B then. If we say, well, some A's are not B's, the negation of that would be to say all A's are B's. If we say, okay, well, all A's are B's, then our negation would be that some A's are not B's. And if we said no A is B, then our negation would be that some A's are B's. And so you can look at this chart and kind of verify that if one of the statements is true, its negation would always be false and vice versa. But let's look at some real words because sometimes that could be kind of confusing. So here's some real statements. So we want to make the negation of the following. So the first one says, all statements like hamburgers. Okay, so then the negation of that would be some students don't like hamburgers. And it follows from the chart, but let's think about why this is true. So, why this is the negation. So if I told you it's true that all students like hamburgers, then if you think about this statement, some students don't like hamburgers, that would have to be false because we just said that all students do like hamburgers. Let's go the other way as well. If it was false, that all students like hamburgers, then it would for sure be true that some students don't like them because that's why it's making that statement false. So you can see that they're always going to have those opposite truth values. So let's take a look at the next one here. We have some people like math. So then we could say that no people like math would be its negation. So again, some people like math. If this is a true statement, then it would be false to say no one likes math because there's a few that do over there. On the other hand, if it was false that some people like math, then it would be true that no one liked math. So you can kind of see again that opposite truth values. So then the next one, some cats do not have 9 lives. Then we could say, well, all cats have 9 lives, and you can verify that those will always have opposite truth values. The next one we have is all squares are rectangles. We could say some squares are not rectangles. For the last one, we have some people have blonde hair. So there's a few different ways we could say that. We could say that if some people have blonde hair, we could say that no people have blonde hair. Again, you can verify those, that they'll always have opposite truth values. Now, the next word that you see here is a compound statement. And so that's going to be looking at the statements that we've seen so far, like Dr. Noah is tall, but it's going to combine 2 or more of these statements together, and we call that a compound. And the way that we can combine them, well, one way is using this thing called a conjunction. And a conjunction is really the more common word and that we're used to seeing. And the symbol that we're going to use is kind of this upward arrow to represent that. So a conjunction can only be true if both statements are true. So like just kind of thinking about in real life, if I told you that my husband made dinner, so my husband did dinner and he did the dishes, the only way that this statement could be true is if he did the dinner and he did the dishes. Then the and would be true. Okay, so let's think about that in terms of this P and Q. So P is just going to be any statement, and Q is going to be, again, some other statement. You see the conjunction symbol in there meaning and. And so we want to write all the different ways that our P could happen. And our P can happen, well, it could be true and Q could be true. Or P might be true and then Q could be false. or P is false and Q is true, or P could be false and Q could be false. So there's really 4 different combinations that you could have here. Traditionally, books will have your first statement being like half of the truths and then half of the falses. And then your second statement, they just kind of like alternate through. You could see there. So now what we want to say is, when is it that P and Q is true? Well, P and Q is only true if both statements are true. So it's only going to happen in this first row. The rest of these are going to be false because they don't have both statements happening to be true. Okay, we're going to look over at disjunction. So disjunction is a fancy way to say or, and it has that arrow, but this time it points down. So that's going to be or. These symbols might be familiar to you if you've seen the symbols intersection or union, which we'll investigate a little bit more later. But we'll see intersection, if that's kind of a familiar word. We would say that that's and it looks like that symbol. Or union, which would look more like that. So a disjunction is false if both statements are false. Otherwise, it's true. So again, if we think back to the idea about my husband doing the dinner, let's say, or the dishes. If I tell you that he made dinner or he did the dishes, well, that could mean that maybe he did dinner and he didn't do the dishes. Maybe he didn't do dinner, but he did do the dishes. I would say those are true statements because it's like either or. But another condition that happens, and we don't always think about it, but if he did the dinner and also did the dishes, that one would also make that a true statement. Okay? So let's look at that. If this is true, true, false, false, Q would have to kind of alternate here. True, false, true, false. So what we're saying with the or is that it's true all the time as long as you have at least one true in there. So the only time it's false is going to be the last one because it's like none of those things happened. Okay, looking at the example, it says we want to make a truth table for, and so it has this compound statement. We see that it has, the first statement is P, then we have that V, remember that's the or symbol or disjunction, and then we have that little squiggle, remember that means not, or is the negation. So since we only have one big statement here, P, we don't have P and Q or P, Q, and R, which you'll see in a little bit, I'm just going to write P, and the only ways that P can happen is it's either true or it's false. So now we have a couple other parts. We're looking at P or not P. Okay, so then not P would end up being the opposite truth values of P. So we'll have a false and a true. Now for the disjunction for our or, we're going to have to put those two parts together. And remember, or is true as long as one of them is true. So this is going to be true and true. So what we've just created is our truth table for that statement. But we needed those 3 parts to complete it. All right, we're going to look at another way that we can combine statements, and that's with the conditional, also known as an implication. And our notation for that is this forward arrow. So we would say if this first statement happens, then Q happens. So since we have our 2 statements, let's write all the different ways that P and Q could happen. So it could be true and true, it could be true and false, it could be false and true, and then false and false. And again, this is kind of just the standard way that you first write out your P and Q in your table. So one way that I think about the implication is kind of thinking about it in terms of a promise. And so you're saying that if P happens, then this thing happens. So of course, if P really does happen, it is true, and Q happens, it's like you followed through with that, so this would be a true statement. Now, if the first thing happened, but then you have a false here, it's like you didn't follow through, then we're going to have a false. Now, since P is false, it's like it doesn't really matter. No promise is broken, whether you did do that second thing or not. So this would be a true statement, and then same thing down below. For example, let's say that I promise you that if I get a raise, I'll take you out to dinner. So if there's a raise, then I'll take you out to dinner. So if I do get a raise, which is what the first statement says, if I have a T and I do take you to dinner, then I kept my promise. Now, if I got a raise, which is what this next statement says, but I didn't take you out to dinner, that means I didn't keep my promise. Now, if I didn't get a raise and I took you out to dinner, I'm just a nice person because I didn't even get a raise. There was no promise that was broken, so it's still a true statement. For the last one, again, if I didn't get the raise and I don't take you out to dinner, there's no promise broken, so it's still going to be a true statement. So the only one that breaks the promise is this second row, because they did get the raise, but they didn't follow through. So that's one way to think about the conditional. Now, there are some related statements to our conditional, and that is that there is the original statement, we already have that, but there's something called the converse. Really, that's just a flip-flopping of our statements. We have an inverse, that's just negating both of our statements and still continuing with that implication. And contrapositive is doing both. It flip-flops and it negates. And so there's some interesting things that happen within our truth table about which of these statements are equivalent to each other. So let's look at this statement. It says, if you build it, they will come. So the converse is again flip-flopping. So let's say that we called P the statement, you build it, and Q is they will come. So if you build it, then they will come. So the converse is going to put the Q part. It's going to say, if they will come, then you build it. So you can see how the P and the Q got flip-flopped there. Now for the inverse, we're going to keep their original order, but we're going to put some negation in there. So we're going to say, if you don't build it, oops, so there's our negation. So if you don't build it, then we say they will, and here's our negation, not come. And then last, for our contrapositive, that's doing both again. So our order flip-flops and it negates. So I'm going to kind of lean towards my converse and then just throw in the negation. So I'm going to say, if they will not come, then you won't build it. I guess following with my order, let's put the won't in red so you can see that negation there. Okay, so what we're going to do is put together our truth tables and what we've seen about the truth tables for the conditionals and negations, conjunctions, and disjunctions to try and prove if some statements are logically equivalent. That is, that we have a tautology. So if you look at example number 6, we want to show that the left side of the equal looking thing, that means tautology, has the same truth values as the right side. So we need to make a truth table for each one of those. So we have the statements P and Q. So I'm going to start by writing those guys and the corresponding truth values that I'm kind of getting used to. So I'll have true with true, true with false, false with true, and then false, false. So those are kind of the standard starts for those. Now looking at the left side, P implies Q. Remember, that's a conditional. The only time that that's not going to be a true statement is if they break the promise. So I have true implies true. That's true. This is the guy that doesn't work. True implies false. That's breaking the promise. Remember, false can imply true. It doesn't matter. And false can imply false. It doesn't matter. There's no promise to be broken because the original statement of the if part, which is sometimes called a hypothesis, is false. So this is what we have going on the left side. Now on the right side, it's going to require us to do another conditional, but look at what it's taking to the conditional, these two negations. So we have to find out the truth values for those first. So remember, negation Q means it's going to take on all the opposite truth values for statement Q. So statement Q goes true, false, true, false. So not Q would have to go false, true, false, true. Similarly, negation P would have to go, instead of true, true, false, false on that first column, it's going to go false, false, true, true. Now, what we're concerned with next is the implication. We want to look at not Q implying not P. So really that's taking a look at what's going on with these two that we just came up with. And so implications are only going to be false if a promise is broken. So false, false, that's okay. True, false, that's the bad one. False, true, that's okay. And true, true, that's okay as well. So finally, what we're comparing, the left side of our kind of equation or our statement, we want to show that it's the same truth values as the right side, which you can see that it is. That's our check. So if you haven't tried some of these truth tables yet, you should take a look at example 7 and 8, which basically prove De Morgan's laws for logic. So they will for sure work out for you to have the same truth values, but you should try it first. Pay close attention to the symbols that are being used. We have a conjunction and we have a disjunction in this one, and I think it flip-flops in example 8. So you should pause, try it, see what you come up with, and then slowly check back in with what's here. Okay, so we're going to get started. Again, we only have the statements P and Q, so I'm just going to copy that down because that's nice and easy. True, true, false, false, true, false, true, false. And so when I look at the left side, one of the things that stands out to me is the parentheses. So it really makes me want to calculate that first, those truth values. So it wants P and Q. The only time the and statements are true is if both are true. So this would be a true, false, false, false. And again, I'm looking back at these statements and looking at them on the same rows. Now it says to negate that. So if I want to negate that, it has to have all the opposite truth values that I just wrote down. So it'll go false, true, true, true. So I've just come up with the left side of this statement's truth values. Now I want to move over to the right side. Now on the right side, it has a negation P and a negation Q with the or. So I need to now figure out what negation P and negation Q are. Negation P has to look back at the very first column and change all the truth values. So it'll go false, false, true, true. Negation Q will look at the second column, and again, they got to switch all the values. False, true, false, true. And so now what we're concerned with for this last part is the disjunction, not P or not Q. Now this is true all the time as long as you have one true. So if we're looking now at these guys right here, the first row has to be false because neither of them are true. Then we're going to get a true, and a true because there's at least one true in each of those rows. So this again is the right side. So if we show the right and the left side have the same truth values, then we've proven that this is for sure a tautology. Okay, now looking at example 8, it looks super similar except the ors and the ands are kind of flip-flops, so let's pay careful attention. But we start the same way. I see two statements, P and Q, so I'm going to write down all of the different ways that those guys can happen together. And then I'm going to look individually at each side. So the left side, and then I'll look at the right side. So the left side wants us to look at, looking in the parentheses, P or Q. So the or means at least one has to be true. So the first one is true, second row is true, true, and then false. So now we're going to negate that. So negation P or Q. That's going to be all the opposite truth values for what we just found over here. So we'll have false, 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 true. So this is what the values are for the left side. Now for the right side, again, it's a conjunction. So we have and, but we're going to and the not P and the not Q. That's what we want to put together. So not P is the opposite truth values of that first column. So false, false, true, true. Not Q is the opposite truth values of the second column. So we'll have false, true, true. And we want to find the actual value of not P and not Q. So that's only true, and statements are only true if both are true. So if we have false and false, that's going to be false. We have false and true, that's false. True and false, that's false. The last one, true and true, yay, we got a true one in there. And so we have the truth values for the right side of that statement, and these are the same. So we have a tautology. It worked out. Right. Another term that we see in logic is biconditional, and really that just means conditional two ways. So bi, like bicycle, two tires. So we can kind of see that it goes both ways by the double arrow that it draws. But really it's saying that we want P implies Q, and we need Q to imply P, like going back and forth. Which is really just saying that we want the conjunction of a statement with its converse. So conjunction being the and the converse being that flip-flop, the Q going to P. And we read that as P if and only if Q. So if and only if. So to build a truth table to see when this is true, I have already actually written out the statement that we want to look at. And so in order to find the truth table for that, again, we're going to need P and Q. That's true, true, false, false, true, false, true, false. And we want to find out both the conditional, and then we want to find out the converse, what the truth values are. So looking forward, basically, true to true is true, true to false is the false one. False to true is true, false to false is true. Now going kind of the other direction, which is what Q implies P, true to true, that's true, no broken promises. False to true, no broken promises. True to false, there's our broken promise. False to false, that one's going to be true, no broken promises. So then for our conjunction, for the and, it's where are both of these things true. So looking at the first row, we have both true, so that works. The second row, we have a false and a true, so that's going to be false. The third row, we have true and false, that's false. And then lastly, we have true and true, which is what we need for a conjunction for both to be true, so we write true. So the only time that biconditional is true, you can see here, is going to be when we have both P and Q being true, or both P and Q being false. Okay, for the last bit of this video, we're going to go back to the diagrams from the very beginning to kind of look at some valid reasoning. So when we see the statement, all A are B. Go back to my pen. What that means is if we look at the set of all things that are A, since all A are B, they're going to live in the set of B. If we say that no A are B, that means that the A will not be inside the B or vice versa. If we say some A are B, that doesn't mean all of them. So just like a part of those things that are in A will have to be with B. So we're talking about like people that live right inside there. Those are some of the A that are B. Now it says some A are not B. That's, again, the same kind of picture, but we're talking about the guys that live out here. Those are A, and they are not B. So for these last couple examples, we're going to draw a picture to determine if the reasoning seems valid or not. So for example 10, it says that we have this hypothesis. All dogs are animals. Goofy is a dog. Goofy is an animal is our conclusion. We want to see if that's like valid reasoning, if that makes sense. This is the very beginning of logic here. So it says all dogs are animals. So if we think of the set of all the dogs, and they're all animals, they're going to live inside the animal group. Now it says Goofy is a dog. So if Goofy's a dog, then Goofy's going to live inside the dog circle. And so you can conclude just looking at the picture that, of course, Goofy has to be inside the animal circle. So that's valid. So what we mean by valid is, does the conclusion follow and unavoidable from the hypotheses? That is it impossible to draw a picture that satisfies the hypotheses and contradicts the conclusion? This is the only way. So that would be a valid argument or valid reasoning. If you look at example 11, let's see if this is valid or not. It says all squares are rectangles. So the set of all the squares, which, by the way, a square just means that it has all four sides are equal. And there's 90 degrees, that's a symbol sometimes, and all the sides are equal. These are actually rectangles. It might sound kind of funky, but the only way to be a rectangle is to have the 90-degree angles, which we have, but it has opposite sides are equal. They don't all have to be equal, but opposite sides are equal, which a square does satisfy that, by the way. All right, so we just wrote the first statement. We have our picture. Now it says all quadrilaterals are polygons. So quadrilaterals, if you're not sure about that word, it has this little prefix here, quad, meaning four-sided shapes. So if you look at this, we have squares and we have rectangles. Those are four-sided shapes. This is actually kind of hidden information, but they must all be polygons then, because it said that all quadrilaterals are polygons. So we took care of that second statement. So it wants us to conclude all squares are polygons. And of course, it has to fit like that because of where the squares is fitting in. So we would say that's valid. There's no other way to draw that picture. Okay, we have one more here. Example 12. We have, if a student is a freshman, then the student takes math. Jacqueline is a sophomore. Can we conclude that Jacqueline does not take math? Let's draw a picture to help us out. So it says, if you're a freshman, then you take math. So think about all the freshman students and all of those guys. It says, if you are one of these, then you take math. So that means you got to live inside the circle of math-taking people. So these are all the people that take math. Now it says, Jacqueline's a sophomore. So we know that Jacqueline does not live inside the freshman circle. So Jacqueline doesn't live there. But she could live here, or she could live outside of there. So she could take math. If she's living in here, she takes math. If she's living out here, she doesn't take math. So she could live in either place. So the conclusion, it says, Jacqueline does not take math. Well, we don't know, because she could live here or she could live here. So we would say that it's invalid. All right, and that's all we got for logic.